This is the course textbook. Um, every course has a classical textbook, a textbook that many researchers and professors around the world agree that it is the textbook. And in your case for this course, this is like the textbook. It's called Introduction to Algorithms by Corman and Company. And these are actually all professors in MIT. It's a very, very popular textbook, though it is a little bit difficult to read. This is a textbook that I would always recommend a student to have a copy of, not just for this course, but for your future computer science job. Whether you work as a programmer or as a researcher, you will keep referring to this textbook. So it is intended actually for undergraduate introductory course to algorithms like this course. And it's also used in graduate courses that teach algorithms. And it's also used heavily in the industry, where people refer to it for the basic principles related to designing and analyzing algorithms. So it's a must-have, in my opinion, for any computer science student. I will also provide a set of additional references, very also popular textbooks, and those will be included as pointers or references in the last lecture slide of the PowerPoint for every lecture. And I will designate the chapters and the specific pages in each chapter that you need to read. The course lecture slides I obtained from a number of textbooks, and I have made many modifications on them. That's why if you noticed, I'm referencing and acknowledging other authors of these slides as well as myself. They will be available in the course website on MET. So I will also try to put all the lecture slides from the beginning of the semester. So what are the learning objectives of this course? Let me first emphasize that this is a very, very important course for your computer science education. It is actually one of the most important courses that you will study, because this is what differentiates you from anyone who took a couple of programming courses in any institute that is not a university. So nowadays, it's very common that people switch careers and move to software development as a more potential, more financially rewarding career. But what these do is they usually go and take a number of courses, usually a tailored certificate that teach them how to program. But in such certificates, you will never find an analysis and design of algorithms course, because this is hard to teach. The concepts are a little bit hard to understand, and they require really a computer science mentality. They require someone who has been prepared through the math and physics courses and the logic courses and the theory courses to be able to effectively consume the material in this course. So while anyone can program, not anyone can think as a computer scientist. And this is the course that makes you think like a computer scientist. Okay, it is not generally an easy course, as I would honestly describe it, but it's a very important course. A lot of the topics we discuss in this course actually will come to you as interview questions in big companies like Facebook and Google and Microsoft and so on. This is what they actually ask about. They don't ask about your ability to write a bunch of nested for loops or a set of nested if statements, or that you use a framework, say like Express or the Node framework in JavaScript. But what they ask about is, can you actually come up with a clever design for a hard problem? Or can you analyze how efficient is a specific solution to a given problem. So by the end of this course, you will have learned the following: how we design efficient algorithms, and this is what we start with in the course. We talk about the different design approaches that do exist, and how you can actually analyze the performance of any algorithm given to you. So we will cover all the major algorithm analysis techniques. This will include asymptotic analysis. We will talk about the master method or the master theorem. We will also talk about a broader algorithm called, a broader theory called Akrabazi. And also we will look at algorithms that employ randomness, and we will use randomized analysis, which is based on probability, to analyze the performance of such algorithms. And we will also look at a very special kind of algorithms which do what we call amortization. We will describe that later on, and we will study amortized analysis. Now, the very important underlying principle that is covered in this course in many places is what's called algorithms complexity. This will become very clear and very important when we talk about the analysis part of the course. So generally the course is divided into two almost equal components. In the first component you learn how you design an algorithm, and in the second component you learn how you analyze. And analysis is all based on the theory of algorithm complexity, so we will come to that. But you have already been introduced to this from the early days of your courses in the university, but now we will talk about it more formally, and we will define what does it really mean. So these are the topics that I'm going to discuss in the course. The design part include covering the three major algorithm design approaches: divide and conquer, dynamic programming, and greedy approach. And in the analysis, as I mentioned, we are going to cover asymptotic analysis, probabilistic analysis, and amortized analysis. We will also cover a number of techniques that I have put here under the titles recurrence and master method. These will be used to analyze the performance of recursive code. Because of their very special nature, we will need a special approach to handle their performance. Along the way, we will talk about a number of algorithms, specifically sorting algorithms. We will also talk about graph algorithms and a number of data structures, including splay trees, skip lists, and towards the end of the course, I cover also tries and heaps, and if time permits, there are more data structures to be covered. I'm not really particularly interested in the data structures themselves. I'm interested in their design or their performance, and usually the performance is more important. So when I talk, for example, about splay trees later on, you will see why, because the analysis of splay trees will involve using concepts that we have learned in amortized analysis. When I talk, for example, about hash tables, I will not be really interested to teach you again hash tables. You've learned it from CS3 days. But I'm interested in the behavior or in the analysis of hash tables. So there we will employ probabilistic or randomized analysis, and we will also employ amortized analysis. So if you remember from your early days, you were told that hash tables are great. They are O of 1 data structure. That is true, but what was not told to you is that this O of 1 is actually amortized. Probabilistic O of 1 is not really asymptotic O of 1. And later on, this will become clear when we spend some time on the analysis of hash tables. Now, if you actually ask your fellow students, colleagues about this course, they will tell you many things. Hopefully they're good things, okay? Especially about me. But the point is, they will complain from the course difficulty. They will tell you they are happy they got like a C or a B in the course. Okay? I mean, the average students. The good ones will tell you, oh, it's a good course and I got a good grade. But most of the students will complain. So let me tell you why students will complain. This course is based heavily on math. But it's not a straightforward direct application of math. I'm not asking you to solve a differential equation and the issue becomes, can you solve differential equations, or do you like differential equations or not? This is a computer science course. So you need to think logically to design a solution for a problem or to analyze a given solution. But when you're doing the design or we're doing the analysis, and especially in the analysis, you need to have some mathematical background, mathematical education that you have obtained and you did obtain in previous courses. You need to know how to solve summations. You need to know what are logarithms, what are exponents, how you can manipulate logarithms and exponents. And you need also to do some proving, although this is not the type of proving that you do in the theory course. There it's more formal. Here it's a little bit informal, but you need to know about proving. And you need some basic probability knowledge. Okay, you need to know what is the meaning of random variable, or what's the expected value of some random variable, and you need to manipulate that variable mathematically in a correct way. So for this purpose, what I do every semester, from the first lecture as you're hearing now, I will provide material that you have to study that will act as a refresher for what you have learned before in Math 1, 2, 3, and 4. And it will cover all the stuff that is related to this course. So I'm not going to give you a revision of all the math knowledge that you've gained or all the textbooks that you've seen, but I will just give you documentation that specifically focus on the parts of the math courses that is used in this course. And even though this will not show up as a serious requirement except in the second part of the course when we talk about analysis, what I'm telling you up front is use the time from here till we reach to that second part to review your math and to make sure that you are capable of solving problems for any one of those four types of mathematical theories that I'm presenting here. So don't wait till the analysis part. Let's go to algorithms design. If I give you a problem, whether it's trivial or complex in its description, what you're going to do to design a solution is to follow one of the four known design techniques. The first one you've already been doing, which is what's called typically brute force. From your first ever problem that you've seen in CS1 going to CS2, passing by CS3, you've seen many problems. Some of them were really difficult if you remember from the quizzes and the midterm and the exam. Your approach is generally classified as a brute force approach, unless by accident actually you were doing something else and you didn't know that you were doing something else. But in most cases, if actually you are just thinking of the solution as a sequence of steps without any structure to your solution, like you say, I'm going to do this while loop to search for something, and then I will have a hash table or a linked list to keep track of what I'm actually processing, and then later on I will come up and from this loop with my, say, set of candidate answers, and then I go into look into my candidate answers. So that's another for loop, smaller for loop. What you're basically doing is you are thinking in a what's called a sequential fashion of the solution. So you develop it from the first step you think you should be doing, and followed by the next step you think you should be doing, followed by the third step you think you should be doing, all the way until you're done. Okay? So basically, your code will end up being just a bunch of for loops and if statements nested inside each other. And you could be writing a solution that will work, that makes sense, that's somewhat, elegant. But it's still brute force in the sense that you are not really following any one of the other three techniques. Okay? Now, what are the other three techniques? The first one we're going to look at is divide and conquer. The second one is called greedy. And the third one is dynamic programming. And when you learn about them, you realize, okay, I've never done this before. I wasn't doing it that way, at least. Okay? And yes, of course, because this is why you have this course. These techniques are not very intuitive. It took a while, actually, to discover them and to use them properly. And the reason why we have three of them is that because for a given problem, one of these techniques might be better either to build a solution with or sometimes to understand the solution. So let me clarify that. Why again do we have three techniques? For any given problem, I could design a divide and conquer solution, a greedy solution, and a dynamic programming solution. Now, those three solutions will achieve what I'm trying to do, which is to solve the problem. But they will not necessarily have the same performance. That's number one. Number two, each one of them is a different way of thinking. So they will be logically different. When you look at the code, they will be logically different. They're doing the same thing, but the code is quite different. Okay? Now, the third thing is, for a given problem, sometimes it's much easier to actually come up with a divide and conquer solution than to come up with a greedy solution or a dynamic programming solution. For another type of problem, it might be straightforward to develop a dynamic programming solution, which I mean by that a solution that is based on the concept of dynamic programming. But it is actually much harder to come up with one that is based on the greedy or using the greedy technique or the divide and conquer technique. The first technique we're gonna look. Divide and conquer is actually a technique that however, Julius Caesar goes into Gallic land and keeps conquering one village after another. Gallic tribes realize that they need to reunite together to fight the Roman army, and they gather in an area that is called, or a province that is called Alesia. The Roman army arrives, and instead of going into battle right away, the Julius Caesar asks his army to build a fence around the Gallic tribes. His plan was to basically starve them, because if you cut their supplies, you cut their supply of food and supply of weapons, then ultimately you can conquer them. That was his thinking. What happens next is very interesting. The Gallic tribes all hear about the surrounded and isolated fellow Gallics in the province of Alesia. So they start moving from different regions in France towards Alesia, and Julius Caesar gets a tip that other tribes are marching, and this obviously presents a challenge to him, because while he can easily fight the guys inside, the problem will be that the tribes coming from different directions will attack his army from the back. So this is actually the moment in history where Julius Caesar shows his ingenuity. He asks his army to build another fence around the Roman army. So the situation now, as is shown here in the slides, you have the inner fence surrounding the Gallic tribes, and then the Roman army is between the inner and outer fence. The outer fence is preventing the marching tribes from uniting with their fellow Gallics in Alicia. And what you're actually looking at here is the most famous example of applying divide and conquer as a war tactic. If you actually think of it just for a while, the Roman soldiers must have been surprised and even shocked by Julius Caesar's decision to build another fence, the outside one, because this means the Roman army is now isolated within the two fences. So it's against common sense. Why would you surround yourself with two fences? Because usually you would want to be outside the fence, not within a fence. But it's quite ingenious, and this is really what divide and conquer is all about. Instead of facing one big Gallic army, what he did by building the outside fence is splitting the Gallic armies into two. There is the inner Gallic army and the outside Gallic army. Now, the inside Gallic army is under the mercy of the Roman dudes, because there is no water going through them, there is no food, there is no weapons. And the outside Gallic army is not capable of helping the inside guys, and is not capable also of launching attacks against the Roman dudes, because they have to cross the wall. And the Romans were really good in building fences, by the way. So it was difficult by the technologies that existed thousands of years ago to just jump over or build a mechanism to actually climb over the Roman typical Roman wall. So what actually happened, because he has applied divide and conquer in such a smart way, obviously he was able to defeat the inside Gallic army first, because they basically ran out of supplies. And they surrendered. And when they surrendered, obviously the outside guys were quite upset, and they felt that the Gallics were defeated. So some of them retreated to the countryside, and others tried to fight, but the Romans were, fortified behind these outside walls. And usually the Roman technique was to get a lot of food and water with them, so they could stay inside the wall for months and months. And ultimately, the Gallic guys outside just disappeared. And he obviously conquered France, and then a few years down the road, he became what is everyone know as Caesar, which was the title he gave himself. So this is where divide and conquer, comes from as a military tactic. Now the question is how to design a divide and conquer algorithm or a solution for any given problem. Okay? Here are the steps. The first thing is you have to divide. And divide here, and this is the nice thing about this, the common sense approach to division usually is the one that will win. So if I give you an array of 1,000 elements and you'd like to come up with a new divide and conquer technique to sort the array, then you have to divide the 1,000 into smaller arrays. Okay? If I give you a map and I tell you search in the map, and instead of searching in the map, you search in regions of the map. So you divide the map into smaller regions. Whatever that is given to you, you have to divide. And the division is done according to the type of the data given to you. So if it's an array and I'm telling you it has 1,000 elements, then your division as a first step is going to be maybe dividing it into 2 sub-arrays. Each one has 500 elements. But if I give you a map, it does not make sense to talk about an array. If I give you a map, if the map is 1,000 kilometers by 1,000 kilometers, then you divide it into regions. Maybe every region is 100 kilometers by 100 kilometers. Okay? So the division step in any divide and conquer algorithm should be relatively straightforward. It is about dividing the problem that you're trying to solve or the data associated with the problem you're trying to solve into smaller sub-problems or sub-components. And usually you will be able to do the division when you're starting just to doing divide and conquer. You in most cases you will be able to do the division. You just need to train yourself on few problems, and then you'll understand the idea. I have to divide. Okay, I have to split what's in front of me into smaller pieces. Now, the second step, which is conquering, is a little bit more challenging, and you will need to get a little bit more training compared to the divide. The second step, which is often called the conquer step, where you solve the sub-problems that you have created in the first step. Now, why this is a little bit tricky? Because what we are after is to be able to solve the problem at hand with the smallest possible effort computationally. So what that means is you have to keep dividing and dividing, applying step one over and over again until the sub-problem that you're dealing with is so simple, it's so easy, it's almost trivial. And then you conquer it by solving it. Okay, so let me give you an example again from sorting, since this is the thing that you got most exposed to since CS3 days. If I tell you sort an array of 1000 numbers, well, 1000 numbers are a lot. So if you do the divide step one time, then you're going to divide the array into two sub-arrays, each of 500 numbers. But still, sorting 500 numbers is not trivial. It will require, considerable computational effort. So it's not enough to apply it one time. So what you're going to do is you can think that, okay, instead of sorting 500 elements or 500 numbers, I'm going to sort the smaller size. So instead of sorting an array of 500 numbers, I am going to sort two arrays each of 250 numbers. Well, this is actually, you're now improving now, because you started with a number, with an array that has 1000 numbers, and then you split it into two, so now you have two arrays, each consists of 500 numbers, and then you split each one of those 500 numbers into two, so now you have two arrays, each of 250 numbers. But again, sorting 250 numbers, now you have four sets, each set is 250 numbers, is again not trivial. Okay, trivial means you're going to do a very small comparison, a very small number of comparisons, or a very small computational effort. 250 numbers, to sort them, that's not a trivial effort. You're still going to do a lot of work. So I will keep splitting them again. So instead of 250, it's going to be 125, 125. And I keep doing that, dividing over and over and over my problem space, until I go to a trivial case. And my trivial case here, actually, if you think of sorting, is that you sort two numbers. You got this like 5 and 10. Are they sorted? Oh, you're happy. Or you get a 10 and 5. Oh, they're sorted, not sorted. So you switched 5 and 10 to become, you have 10 and 5 as input, you switch them to become 5 and 10. So this is an example of what we call a trivial solution. In fact, in case of sorting, the trivial solution or the trivial problem size is 2. You have an array of 2 values. Okay? You can even go more trivial by saying 1, but 1 does not really make a lot of sense. We will actually see it later on in some of the algorithms we're going to look at. But if you're thinking of this for the first time, and instead of sorting an array of 1000 numbers, let's actually sort an array of 2. And sorting an array of 2 is really easy. It's just a single if statement. If the second is smaller than the first, then swap the second with the first. So this is what we refer to as conquering. To conquer, you have to be working with a really trivial problem. Okay? Now, the third step, I hope now it's kind of, the pieces are falling in place. We didn't really solve the whole problem. If I tell you sort, and I give you an array of 1000, and you keep splitting them until you go to a sub-array of 2, and you sort each one of those 2, you really didn't sort the whole array. And this is really a property. This combination step is a property of divide and conquer algorithms, that when you're conquering, you're not really solving the whole problem in one shot. You are solving a smaller size problem. Consequently, because it's smaller than what you started with, you have to do some effort at the end, which is the combination effort, to put together the different solutions to the smaller sizes so that you have a solution to the problem that you started with, which is in our case here, in our example, the sorting of 1000 numbers. We will see many examples related to this, but I'm just giving you, a systematic way to think of how can you do divide and conquer. Okay? So even though it's called divide and conquer, the steps are divide, 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 keep dividing, that's number one, and then conquer when you reach to a trivial case. And the third step, never forget it, is going to be combine your solutions to the smaller version of the problem to get the solution that you're looking for, which is to the initial problem that you started with. So remember again, divide, conquer, there's always a combine at the end. So this is an illustration trying to show you how we go about divide and conquer. I'm repeating this because from now on, if I tell you use divide and conquer, you have to think this way. Okay? You start the problem, you're not going to solve it, you're going to divide it. You divide it to smaller subproblems. Notice that the subproblem has to be of the same type as the problem. Okay? You don't change the problem. Here I'm referring it as the problem, but you could replace the word problem with data. Okay? So if I give you, for example, an array of 1000 numbers, the division will yield two subarrays, each of 500 numbers. But because of how I'm showing it to you here, what you need to make sure of is that you should never divide it into two arrays where one array consists of 600 numbers and another array consists of also 600 numbers. Because for some reason when you're doing the division, you replicated the numbers. Okay, so if you're going, let's imagine I have the numbers from 1 to 1000. Okay, so, and they're not sorted. So if I say I'm going to split this array of 1000 numbers, then I'm splitting it into almost two equal parts. So if it's 1000, it's going to be 500 and 500. If it is 11, it's going to be 5 and 6, almost equal. Okay, now, but it shouldn't be like if it's 11, I got 7 and 7, and if I tell you like how come 7 and 7 is 14, you tell me like some of the numbers are duplicated in the two subproblems. Okay, what we're doing is we're doing the division to reduce the problem space, and that means is you divide what is given to you, but you don't replicate any of the data. But as I mentioned, we're going to keep dividing until we reach to a trivial case. And this is what chart is actually telling you, that I keep dividing, I keep dividing, I keep dividing until I reach to a point where, okay, I don't need to divide it anymore because the solution is intuitive. It just is falling into place by just looking at the data. Okay? There is a minimal computational effort required. But again, remember that this conquering step is actually a solution to the subproblem, which is the one highlighted here in pink. Okay? It is not a solution to the green subproblem or to the orange subproblem or to the cyan subproblem, the one we started with. Okay, it's just to the pink subproblem. So now I have this, solution to the subproblem after I've reached to a size or the subproblem size that is manageable. I start to combine my solutions to get a solution to the bigger problem. Okay, now from this one note, you should already be thinking of this, that many divide and conquer algorithms will be implemented recursively, because as this chart illustrates, I will generate the solution when I reach to a trivial case, and usually in the recursion that will be the base case of the recursion, and then as I go out from the recursion, I will be doing some combination effort. Okay, but you don't have to do it recursively, but usually it's more elegant to do it recursively, and it's easier in many cases, as you will see, to do it recursively than to actually write the iterative code for a divide and conquer algorithm. So this goes on, after building solutions to subproblems, which is the one highlighted in green here, I will build the solution to the bigger subproblem, which is highlighted in orange, and then finally I get my solution to the original problem I start with. So we are going to see a number of examples that uses divide and conquer. Okay, we are going to see two sorting algorithms, and we're going to also see some advanced examples of divide and conquer from graph theory and from matrix multiplication, or basically linear algebra. So let's look at merge sort. Okay, the first of the two techniques that employ divide and conquer. This is actually what I have been describing to you as a motivational example in the previous slides. Now, merge sort goes like this. In the divide step, I'm given initially an array of n elements. I'm going to say, I'm not going to sort that. I will divide it into two halves. Okay? And then I will keep dividing into two halves. So the 100 becomes 50 and 50, the 50 becomes 25 and 25, 25 becomes 12 and 13, and it keeps going like that. Okay? Now in the conquering, I will sort the smallest subarray I have reached to, and in the combine, I will merge the sorted subarrays from the level before me. So here's an example of merge sort. Okay, so I'm giving this array that has, as you see, 1, 2, 3, 4, 5, 6, 7, 8, 9 elements. Okay, I will pick the value in the middle, and I will split this input array into subarrays. So because here the array size is odd, I ended up with one subarray to the left, which is even, and the right subarray is going to and the right subarray is going to be of an odd number of values. Notice that I'm not doing any sorting yet. I'm just doing the divide step. But if you look at any one of those two subarrays, they're not really trivial to sort, because you got to do a number of comparisons. We want to always think, when we're doing divide and conquer, of the most trivial effort I could be exerting or doing to actually get some answer. So I will apply the divide step again, and I will split the left side array to two subarrays, 99 and 6 on one side, and 86 and 15 on another side. And then I will apply the same idea again by splitting the array that appears to the right in the second row into two smaller subarrays. And again, I'm not changing any values. I'm not doing any sorting yet. Now, merge sort thinking goes like this. We will stop at the most ever trivial case you can think of, which is that you have an array of one element, because an array of one element is sorted by itself, because there is nothing bigger than it and there is nothing smaller than it. So it is sorted. And that's what merge sort, way of thinking, how it works. So I'm working with these individual subarrays, each of size 1. Okay, and because I have this nasty one on the left, on the right, which has 86, 4, and 0, I will, when I split it, it will actually take me one more step to split it. Okay, so now the picture is, as you see, way at the bottom right, you have the 4 and 0 after I splitted them. So now I've splitted the input array into 9 arrays, each of size 1. I got 99, I got 6 alone, 86 alone, 15 alone, 58 alone, 35 alone, 86 alone, 4 alone, 0 alone. Now, all this, as you notice, I am just doing divisions. Now, after having an array of one element, my problem is almost solved. It's actually solved, because there is nothing to be done. This is the most ever trivial thing I could do, which is to do nothing. Because if I say that an array of one element is sorted, then I'm done. It's sorted. Okay? So here the conquering step is trivial. There is nothing. Okay? Now, since it's done, the conquering step, what we're going to do now is the combine. And according to the merge sort way of thinking, all the effort is done in the combination step. Because when we combine, we want to combine the elements correctly. Or, in other words, as the name implies of the technique, we want to merge them correctly. Okay? So I have here 4 and 0 way at the bottom right. It should be 0 and 4. It's not 4 and 0. That's not the right order. It should be 0 and 4. So when I'm merging the array of 1 that has 4 and the array of 1 that has 0 together in the combine step, okay, which in the merge sort technique is called the merge step, in this combination step, I'm going to swap them with each other. So it's going to be 0 and 4. Okay? And then when I merge 0 and 4 with 86, it's going to be 0, 4, 86. So I combine them in the right order. Okay? And when I merge 35 and 58, it's going to be 35 then 58, not 58 then 35. And again, the same thing is going to be 15 and 86, and it's going to be 6 and 99. Okay? Now notice I am now combining solutions. The trick here in merge sort is the conquering is nothing. There's nothing really we do at the conquering step. It's just we go and reach to an array of an element of size 1, and then we assume it's sorted, and then we start doing the combination. And in the combination, we're doing all the work. Okay? Now, this will continue on, because 0, 4, and 86 is sorted, but it's not merged with the other solutions that I have actually developed, which is 58 and 35, 15 and 86, 6 and 99. Okay? So I will merge 0, 4, and 86 with 58 and 35 to get 0, 4, 35, 58, 86. Okay? And the same thing for the sub-solutions on the left. And finally, I will merge these two subarrays that go 6, 15, 86, and 99 with the other one on the right to get the final sorted array. Okay? So you have just seen merge sort. Let's look at another technique just to get your head, around divide and conquer and seeing it applied in many different ways. And really my goal while I'm teaching you algorithm design is to give you as many problems as possible. Each problem will be slightly different, and as you learn all of these algorithms that use divide and conquer, you will see many of them in the lecture and in the tutorials. This is the way you actually learn how to do divide and conquer. So you've seen one way, and I think merge sort is quite straightforward. It's very intuitive in the sense that if you want to sort an array, why don't you split it into smaller subarrays and keep doing that. Let's see another technique, which is quicksort. And this actually has historically been known and still is by many researchers believed to be the most generally applicable sorting technique. So we're not talking about the performance of these algorithms. We will do that later on. Merge sort and quicksort will sort in n log n. We will talk about that later on in detail. But quicksort is slightly faster than merge sort. It's still n log n, but the constant beside n log n in the case of quicksort is much smaller than the constant in the case of merge sort. So this is why this has historically been known as the fastest one. Okay? If you actually Google online, you will see a number of new sorting techniques that could be faster than quicksort in certain scenarios. But quicksort, the nice thing about it is that it is generally fast in all scenarios of the data. Okay, so it's still still a very, very popular sorting technique, and it's the one, by the way, used in inside the Java API and in the Python API. So if you've ever built an array list in Java and you say .sort, it's actually using quicksort. Okay, now let's see quicksort and let's see why it's different. This is still divide and conquer, but it's doing something else than merge sort. So let's read this. So it says divide. This is really the new part here. You pick a random element. We're going to call it the pivot, and you partition the array that is given to you around this pivot. What that means is that you are going to look in the array for all values that are smaller than the pivot, and you will make sure to put it to the left of the pivot. And then you will look again in the array for all values greater than the pivot, and you will make sure to put it to the right of the pivot. Okay? Now, this is a different way, as you notice, in doing the division. In merge sort, we pick the value in the middle and we split at that point. But what we're doing here is that I will roll a dice that will give me a number between 0 and n minus 1, where n minus 1 is the last element in the array because the array is of length n. And that value, or that index that comes out from rolling a dice, I will go to the cell whose index that was the dice output. So let's say I have an array of 100 numbers. So the numbers are going to be stored in an array from 0 to 99. So I will generate, using a random process, a number between 0 and 99. Let's say I got number 71. So I will go to the array index 71 and will find a value. Okay, let's say I looked there and it was like 600. So I'm calling this specific value 600 my pivot, because I'm going to do the following. I'm going to keep all numbers by scanning the array from left to right that is less than 600. I'm going to put it to the left of 600, and all numbers greater than 600 I'm going to put it to the right of 600. Okay, so again here the division is different. Okay, now I will keep doing this division just like we've seen with merge sort until I go to a trivial case. So I will keep rolling a dice, getting a pivot index, going and seeing that pivot in that specific index, and then grabbing the values to be that is less than the pivot, putting it on the left, and the values greater than the pivot, put it to the right, and I keep doing that. Okay, now I know this is not trivial. There's a number of issues here, okay, that you should be thinking of by now. What is the difference between this and merge sort? Merge sort will always split into two equal subarrays, or almost equal. Here this is not, because let's say you pick the number that is the largest number, the pivot was the largest number in the array, so you will have all the elements minus 1 in the left subarray, and the right subarray will just have the pivot. Okay, and let's say you're sorting 100 numbers and the largest number was 600. When you by accident rolled a dice, and you got by accident the 600 being the pivot, all the numbers are less than 600, so all of them will go to the array that is left of 600. And the array that is to the right of 600 will either have 600 and nothing else, or just be empty if you include 600 in the left array. Okay, so here the division is actually not dividing the input array into two equal subarrays, it's dividing it into just two subarrays. We can say that they are equal or close to be equal. Okay, now so that's the first thing that you should already have noticed. Now the other thing is, you might ask, like, why random? Why are we involving randomness here? It turns out actually this is, we would say, it's generally the fastest sorting algorithm because we're using randomness. But I will not go into the discussion of why this is actually better. Now we will see that in the analysis part when we talk about randomized analysis, because this employs probability. Okay, so that's the second observation on this. Okay, now I am really not going to describe exactly how we do things here. We're going to see it in the in the next slides, but I just want to look at the chart at the bottom here that is again highlighting the idea. I got this input array that shows up at the bottom left. It has 1, 2, 3, 4, 5, 6, 7 elements. I rolled the dice, I got the index whose value is x. My task is going to be, if I run this sorting algorithm for just one time, I'm not going to run it for one time, I'm going to run it for many times, as we will see. So again, we're going to go into this kind of divide until we reach to a trivial case. We will see that in the coming slides. But again, to highlight the basic idea here is that, as you see at the bottom right of this slide, the x is in its place, and everything to the left of the x, I'm going to call it the L set, or the L subset is smaller than the X. You could think of the values here represented by the height of the bars. And all the bars in the G set, as you noticed, is longer than X. It is greater than X as a value. Okay? Notice that the G and the L are not sorted. What we just have done is we've moved some of the values in the array from the right of X to the left of X, and some of the values in the array from the left of X to the right of X, just to be able to get the picture at the bottom right, which is everything to the right of X is greater than X, everything to the left of X is less than X. But this does not mean that L is sorted or G is sorted. No, you should by now have guessed what are we going to do next. We are going to apply this same way of thinking to L and G. And we keep doing that until we're done. Okay? Now, if you look here, what should you be confident about if you look at the chart at the bottom right? The only thing that you're confident that you have actually accomplished here is that X is in the right place. And this is a very important observation. What we've just done is we have found the right place of X in the final sorted array, in the final output. Because regardless of what you do to L members, you will never make any one of them exchange its location with X, because all of them are less than X. And whenever you do to the G set, you will not move any member in the G set to be in X's location or before X. What this means is that X is in the right place. But the L and G are not sorted. So we're going to apply the same logic over and over until we're done. So let's see a simulation of all of this. So here is a simulation. So I start my quicksort invocation with the array and the index of the first cell in the array, which is 0, and the last cell in the array, which is 5, because this is an array of 6 values. I will call a method called partition, okay, that will partition this input. Now, we need to figure out where is the pivot. So again, the best performance of quicksort you will get by rolling a dice that gives you a number between 0 and 5. Any other variation, deterministic variation, where you think, oh, why don't I pick the value in the middle, or the value at the beginning, or the value at the end, actually have a counter case where the performance degrades. But with rolling a dice, as we will see in randomized analysis later on, with rolling a dice, you are guaranteed that you're going to get n log n all the time, regardless of the input array. So the question pivot. Now, let's say that my pivot is cell 0. Okay? Now, which is the value 6. Now, what do I need to do? I need to put all values less than 6 to the left of 6, and all values greater than 6 to the right of 6. So here is what I'm going to do. I will use 2 pointers that scans the array from the 2 ends. The left is moving from left to right, and the right is moving from right to left, looking for a violating pair. And when I find the violating pair, I will swap them. Okay? So the left is supposed to be looking at values to the left of 6, which means it's smaller than 6. So if it finds a value that's violating, it's going to be greater than 6. So if the left moves to the right, it will check the 5. The 5 is less than 6. It's happy. We're happy. We'll move on. We go to the 9. And when we see the 9, we stop, because the left should always be pointing to values less than 6. So we will stop at this violating element, the 9, and we stop moving the right. looking for a violating element. We position the right at the last cell in the array, and it's already violating because the right is supposed to be to the right of 6, and the right of 6 should be greater than 6. 4 is not greater than 6. So what we're going to do is we're going to swap these two violating values like this. And then we will continue on until the right and left crosses. So we move to the 3, and the 3 is violating from the right, or the right is pointing to a violating element now, the 3, because the right is supposed to be pointing to greater than 6, not less than 6. And the left is also pointing to a violating pair, a violating value, which is 12. Left is supposed to be pointing to less than 6, not greater than 6. So swap. And now the picture is 3 and 12. Okay? Now, once they cross the left and right, we stop. Okay? And when we stop, we can swap, we will swap the pivot with the area of right. Now you look at the picture now, and I think now it's much better. This is what you want to see, which is all the values to the left of 6 less than 6, all the values to the right of 6 greater than 6. Okay? Now, we're going to return the index of 6 to highlight that this is the current division point. So what we are going to do next, we are going to apply the same algorithm on the left subarray of 6 and the right subarray as well, each separately. That's why we need the pivot position from the previous run, so we know when we call quicksort what are the indices to work with. 6 now is in the right location, so we're going to work on indices from 0 to 2 and indices from 4 to 5 in another call. And that's what this is showing. Whether we include the 6 with the left subarray or the right subarray, it doesn't matter. It will always stay in its location. If we include it in the left subarray, it's always going to be the last value. If we include it in the right subarray, it's always going to be the leftmost value. So it's going to be 6, and then 12 and 9, and then when we sort, it's going to be 6, 9, 12. And we keep doing the same logic that we have described. As you notice here, the quicksort is being called again. So this is, as I mentioned earlier, many divide and conquer algorithms are naturally recursive. We're going to call quicksort again recursively, but from 0 to 3, one time and another time with indices 4 to 5. Now, calling it on 0 to 3, we can imagine that this is actually our input now. Let's play the same trick. Let's do the same logic, the same algorithm we've seen before. We're going to pick a pivot randomly, and then we will sort around or arrange the values around this pivot. Again, I will find a random generated number between 0 and 3 to be my pivot. And let's say I did that, and again I found that the outcome was the randomly generated number was 0, so my pivot is 3. I'm showing you this particular case because sometimes when we pick a pivot, the division will not progress as we will want. If I have here an array of 4 elements, which is 0, 1, 2, 3, ideally I want to, in the next step, be working with 2 subarrays, each one is of size 2. This is not always going to happen, but again, this still works nicely because we are picking a pivot randomly, so the chance actually of getting a bad pivot will turn out to be much smaller than the chance of getting a bad pivot which, as I mentioned before, we will see in randomized analysis. So if my pivot here is 3, let's apply the logic again just to make sure that we are on the same page. Now, everything to the left of 3 should be less than 3. I have nothing here smaller than 3. 3 is the smallest number. And everything to the right of 3 is going to be greater than 3, and it is actually the case. I don't know that obviously in the code until I run the same algorithm we've discussed, so I will use my left and right pointers to find out any violating pair to swap them, and if there is none, then it stays the same. And that's what you see here. Left and right moving, looking for, again, the right moves towards the left, left moves towards the right. We're trying to find the violating pair. There's no violating pair. The right and left, once they cross or they are looking at the same value, we stop and we return the index of the pivot, which is 0. Okay? Now, here obviously the 3 is not going to move away from its location, and that will be the run for array of 0, 3. Okay? Now I'm going to also show you what happens next. I've just mentioned or found in my previous run that the pivot is 3, so I will return that, and that will be my splitting, because I'm splitting, as you see in the quick sort, left and right of the pivot. So the 3 will be alone, and then the right is going to be 1 to 3, and I follow the same logic again. Okay? Now, this will go on for the right array over here, which is the one that says quicksort array of 1 to 3. But for the left subarray, which only has the 3, there's no point in actually going further into recursion because there's nothing to compare. Okay? So we will keep applying the same logic. This is the code I'm telling you about. Okay? It's the same. Now, let's look at the third example of using divide and conquer, but with a little bit of an advanced problem. Now, this problem actually belongs to the graph theory area, and the problem statement is as follows. Given a set of points where every point has x and y, you would like to find the 2 points that are closest to each other compared to all other points. Okay? Compared to all other interpoint distances. Okay? So, this, as I mentioned here, this could be an application or an algorithm that you run on a map, or anything that could be modeled using the same way. So there's even some gene-related problems or genetics-related problems that are modeled as a map, and you'd like to find the closest two genes to each other. Okay? So the question is, how can you go about thinking divide and conquer here? Okay, now it's always a good exercise when you, especially when you're new to algorithm design, to think brute force first, because thinking brute force will tell you what not to do. So let's see the brute force version of this. So here is the brute force version. What you're going to do is you're going to run an algorithm that calculates the distance between every point and all other points. So you pick a point, let's say you have 50 points in that chart we were looking at. You pick the first one of the 50 and calculate the distance between it and the other 49. And then you pick the second point and calculate the distance between it and the other 49. And then you pick the third point and calculate the distance between it and the other 49. So you will have all the distances between any 2 points. You sort them and you get the smallest one. Okay? Now, or you could do it on the fly, like, you keep calculating the distance, which is what this code is showing you. You keep calculating the distance between every 2 points, and you start with a minimum. That's a very big value. And if your the value that you've calculated as the distance between 2 points is smaller than the current minimum, then make it the minimum, which is the typical strategy we use to find the minimum value. But notice here what you're doing is an O of n squared solution. Okay, I've tried to highlight it with the column on the left. You're going to calculate the distance between P1 and P2, P1 and P3, P1 and P4, P1 and P5. And then you're going to go again and calculate the distance between P2 and P1. And then P2 and P3, and then P2 and P4, and P2 and P5. Okay? So notice I calculated P1 and P2, and then later on calculated P2 and P1. Okay? Now, this is brute force. It will work, but this is brute force. And we don't like it to be n squared. Why? Maps or any problem related to graph theory, the volume of data you're working with is usually really huge. So imagine if you have a map that has 10,000 points. That's 10,000 squared processing time. And 10,000 is not really a big number in the mapping world, okay, or in the graph world, okay. So we want to do something better than n squared. And if you want to do something better, then you have to use one of the techniques we're discussing in the course, and here we are actually discussing divide and conquer. So let's see how we go about designing an algorithm that uses divide and conquer. So here's what I'm going to do. I'm given a map, and the points are scattered on the map. A brute force approach means go to every pair of points and calculate the distance. So I'm going to try to limit the number of computations I do by dividing the map into 4 quadrants. And then I will compute the distance between the points in each one of those quadrants. And instead of actually doing a lot of computations, just by dividing it into quadrants, I will decrease the number of computations I'm doing. Okay? Because I will only compute the distances between points within a quadrant. And then I go to the other quadrant and calculate the distance between the points within this quadrant, and so on. Okay? This is the merit of the idea. This is how we apply the divide step. Okay? Now, as I mentioned before several times, when we divide a lot until we go to a trivial case. Okay? Now, if we try to think, okay, what's a trivial case here? Well, it does not make sense to have a quadrant that has 1 point. Because if I'm looking for the distance between 2 points, then a quadrant with 1 point is not really helpful to me. It will not help me in any way to find the solution. So it should be at least 2 if you think of it, so that you can calculate the distance between 2 points. Okay? Now, the problem that you might have already been thinking of, or if you have already read the last point here, the combined step, which is that the smallest distance between 2 points could be crossing on that distance, on that line connecting the 2 points, could be crossing quadrants. So I have to also, when I am merging my results, to take that into consideration. Okay? So again, this is my strategy. Divide and conquer means dividing my problem space or my data into smaller components, which saves me computations. So if I'm giving this big map of points, I'm not going to work on the whole map trying to find the distance between every 2 points. I will split the map into 2 portions. In fact, as I mentioned, we're going to split it according to 4 portions or 4 quadrants. Okay? But let's just imagine that we're splitting it for the sake of explanation only to two halves. Okay? Now, I will compute in every one of those halves, there are a number of points. I will compute the distance between each 2 points in each one of those halves. So let's say after I have done that, I have found that the smallest distance between any 2 points in the left half is 12, and the smallest distance between any 2 points in the right half is 21. Since I'm going after the smallest distance in the whole graph, I will pick the minimum of the two to continue working with. So the minimum of the two is 12, and what I'm going to do next is I want to make sure that this is truly the minimum in the whole graph. Why there is an issue here of concern? Why am I saying I want to make sure that 12 is indeed the smallest in the whole graph? Because there could be a case that there is a pair of points which appears here in the center of the graph. There is a pair of points that exist on both sides, and the distance between them is smaller than the distance I have computed, which is clear here. 8 is less than 12. But I didn't actually, up till now, consider this case. What I have done is I have split the graph into two subgraphs, or split my map into two smaller maps, and I work on every half or submap separately. So I worked on the left alone, and I worked on the right alone, searching for the minimum. I have found that the minimum is 12 on the left, the minimum is 21 on the right. But none of my computations considered the case where the pair is on both sides. So what I'm going to do next is I am going to go to the line dividing the map or the graph, and with the information that I have found, that 12 is the number I'm trying to find if there is a value smaller than it, and I will start considering the points on both sides, having the knowledge that if there is a minimum that is better than what I have found, it has to be less than 12. Now, that means I don't actually have to go and do a brute force approach starting from the center or the line splitting the two maps. Why? Because the largest distance I would be interested in is 12. Okay? The delta that is labeled or that is displayed here in a dark gray color, if my current minimum is 12, then at most I should be looking at 12, regardless of what 12 unit is. It's 12 meters, 12 pixels, 12 whatever, okay? 12 kilometers, but I'm really interested in this dark region whose width is 12, because within it there could be possibly points that are less than 12, but outside it, it's impossible to actually get an interpoint distance or a distance between a pair of points that is less than 12. Okay, this is a refinement on what I'm doing, in the sense that I don't again have to do brute force. So I will split the map. Again, the algorithm goes like this: divide and conquer. Divide means splitting the map into smaller maps or smaller graphs or subgraphs, and then finding the minimum. And then when we're combining our results, we're always going to go back to the line splitting our map or our graph and only consider the region that is equivalent to the found minimum up till now. Okay, so the delta here is going to be 12. Now, within this region, I will look for points that exist within this region, and I will calculate the interpoint distance, or the distance between a pair of points. So I have numbered here all the points I should be interested in. But I hope some of you already are thinking ahead and realizing that we can even do further refinement. For example, should I be worried about the distance between 1 and 5 or between 2 and 7? And obviously the answer is no, because the distance between them is going to be much bigger than 12. Okay? The points that probably are of concern to me are 4, 5, and 6, because it could be between 4 and 5, the distance is smaller than 12, or between 5 and 6, the distance is smaller than 12. Okay, so 4 and 5 and 5 and 6 are candidates. Maybe 1 and 2, I don't know. There has to be a way to quantify that. And the question is there a way to quantify that? How can I omit the comparison between, say, 1 and 5, or 2 and 7, okay, or 4 and 2? And obviously, the answer, I hope you already got this, the answer will come right away from geometry. We can know how far these points are giving their coordinates, and approximately we can figure out, okay, that they will never, distance between them will never be less than 12. Okay, now if you imagine that every one of those points is in a unit distance, so point 30 is in 1 by 1, point 28 is in 1 by 1, and so on, you can calculate from any one of those points how far away you can go to get a value less than your delta. Okay, so this is a straightforward application from geometry. You can do it using Pythagoras, you can do it in a number of ways, but the point is I don't actually have to consider all of these points. Okay, so I can figure out where are my candidates, where are the points that are possibly are less than 12. Okay, I will not know until I compute them, but I will know before doing the computation which ones are impossible to be less than 12. Okay, so that's will be an additional exercise just to limit our comparison space. Now, some of you might be wondering, how much did we improve from the O of n squared performance using this approach? And the answer actually, it's quite improved. I'm not going to go again into the proof of this, but as you will see later on in the course when we talk about recurrence relations, because as you see down here when it says t of n equal to 2 tn by 2 plus O of n plus O of n log n plus O of n, you have not learned up till now in your computer science career how to solve this, but this will solve down to O of n log n. Okay, so this is much better than n squared. Now I will conclude today's lecture by putting you the references that you are responsible for to read for the content I have covered here. I have put scanned copies of the references so you can download and start reading the material related to today's lecture. Thank you. Have a good day.